While studying linear algebra, you may have come across the notion of tensor products. And tensor products lead to the construction of a very interesting algebra called the tensor algebra, which is what I'm going to talk about in this lecture. But before we talk about the tensor algebra, let me recall for you what a tensor product is. So we're going to fix a field F, and all our vector spaces are going to be over F. And let's say V and W are vector spaces, let's say finite dimensional vector spaces over F. And say V has a basis V1 dot 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 Vm, W has basis W1 dot 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 Wn. Then the tensor product of V and W is can be defined to be the vector space. Let's define it, the vector space, F vector space of course, with basis, and I'll just give some symbols, I'll write down some symbols, Vi tensor Wj, where I goes from 1 to m and j goes from 1 to m. So if V is an m-dimensional vector space and W is an n-dimensional vector space, then by definition V tensor W is an m times n dimensional vector space. Now there's something slightly unsettling about this definition. It is that the tensor product of V and W seems to depend on the choice of bases of the vector spaces V and W. So this is of course not something that should happen. The tensor product of V and W should be independent of the choice of bases of V and W. If you change the basis, you should not get a different tensor product for these vector spaces. So let me address that issue and see what happens when you change vector spaces. When you change bases of these vector spaces, you get a different, maybe a priori different notion of a tensor product, but these two turn out to be essentially the same thing. We can identify them. So one important thing to note before we go on to identify them is that you have this, you can define a map on bases, let's say B, which takes Vi comma Wj. So you take this basis, cross this basis and send it to Vi tensor Wj. This extends uniquely to a bilinear map from V cross W to V tensor W. So V cross W is just the Cartesian product of the vector spaces V and W, and so we think of it as pairs, one element in V and one element in W. And how do you define B from V cross W to V tensor W? So what's a typical element of V cross W? So if we have a typical element of V cross W is of the form V comma W, where V is in V and W is in W. So if V is a vector in capital V, then V can be written as summation AI Vi, I goes from 1 to m, expanded in terms of our basis. W is Bj Wj, j goes from 1 to n, and then we can define B of V comma W to be, so it's B of summation I equals 1 to n AI Vi comma Bj Wj, j goes from 1 to, oops, this is m, j goes from 1 to n, and using bilinearity you see that this is forced to be summation, double summation I goes from 1 to m, j goes from 1 to n, ai bj vi tensor wj. So this is the map B from V cross W to V tensor W. This is not a linear map, it's a bilinear map. And it's also not a surjective map. Not every vector in V tensor W is of the form uh, B of V comma W. And this B of V comma W is usually denoted by V tensor W. And this is exactly what it is. Okay, so what I'm saying is that not every vector in V tensor W is of the form little v tensor little w for some vector v in little v in big V and some vector little w in big W. I leave it as an exercise for you to check that when v and w are not, let's say they are two-dimensional vector spaces. Okay, so that's the definition of tensor product, but what happens if we start with a different base? So if instead we used a different basis, let's say v1 prime vm prime of v and w1 prime wn prime of w, then we would get a different notion of tensor product. A priori different notion of tensor product. So it would be, let's call it v tensor w, but I'll put a square bracket to say that this is with respect to square around the cross, to say that this is with respect to these new bases v prime and w prime. And you would also get a bilinear map v prime from v cross w to v tensor w. So this v square tensor w would be the vector space with bases vi prime tensor w j prime, and b prime would be defined exactly how b is defined, except that we would use this other basis. But what I want to say is that these two vector spaces are somehow, these two notions of tensor product are somehow the same. We can identify the vectors in one with the vectors in the other very naturally. So to do this, let's just firstly take vi. So this is an element of v, and so this element can be expanded in terms of any basis of v. So let's expand it in terms of this basis v1 prime v2 prime dot 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 vm prime. So this, let's say, is equal to k goes from 1 to m a ki p prime k, and similarly let's say wj is summation l goes from 1 to n b lj wl prime. Okay, so now what do we have? We have, I'll draw it somewhat schematically. One thing we have in common for both these definitions of tensor product, v cross w, that is not changed. And then we have these two notions of tensor product, v round tensor w, and then there's this bilinear map b, and then we have this other b prime, and we have v square tensor w. And I want to say that these two are related in the sense I'll give you an isomorphism phi from this vector space to this vector space, which will make this diagram commute in the sense that phi circle b is going to be b prime. And what is this phi? It's not difficult to write down. Phi, I'll define it only on basis vectors of vi tensor wj, and it's suggested by these expansions. It's just going to be summation k equals 1 to n, l equals k equals 1 to m, l equals 1 to n, a ki b lj v prime k tensor w l prime. This is sort of forced by requiring that b prime is phi circle b. And so this is a unique map from here to here, and you can construct its inverse in the same way. You use the expansion of the v prime basis and the w prime basis in terms of v and w bases respectively, and construct a map going the other way. And It's going to be an inverse for this map. So these two vector spaces turn out to be isomorphic. Okay, we are not going to in any serious way use these notions. There's also something called the universal property of the tensor product, which I won't go into right now. But in some sense, tensor products are basis free. Okay, but for us it's enough to just think of the tensor product of two vector spaces in terms of basis. You have a vector basis of these two vector spaces, then the tensor product is somehow a vector space with basis, sort of a Cartesian product of the bases of the two vector spaces. This notion of tensor product can be applied to several vector spaces. So suppose you have V1, V2 up to VR are vector spaces, and let's say Vi has basis V11, let's say Vi1 up to Vi Ni. So the ith vector space has dimension Ni for I goes from 1 to R. Then V1 tensor VR can be regarded as the vector space with basis V1I1 tensor VRIR, where ij lies between 1 and nj for j equals 1 to r. This is a vector space whose dimension is the product of the dimensions of the vector spaces v1, v2, vr. And it's not difficult to see then with this definition that if we have vector spaces v1 up to vr and then a few more vector spaces vr plus 1 up to vr plus s, then v1 tensor vr, we take this tensor and then tensor it with the other tensor vr plus 1 tensor vr plus s. This is the same as the vector space v1 tensor all the way down to vr plus s. So this is just, because these things essentially have the same basis. Just think about it a little, it's quite clear. Okay, so now let's apply this to a single vector space V whose tensor product we take with itself repeatedly. So now given a vector space V, let TV, let's say TdV, we define to be V tensor V tensor V tensor V, this taken D times. Okay, and what we have is that TRV tensor TSV is isomorphic to TR plus S. It for all RS greater than or equal to 0. At this point I should say something about what is T0V. So T0V, we will take it to be by definition just F, the one dimensional vector space F over F. And now we are ready to define the tensor algebra. So this is the algebra TV. It is defined to be an infinite direct sum d goes from 0 to infinity t dv. So this is the tensor algebra as an additive abelian group. It's just an infinite direct sum of vector spaces. And how is product defined? So product is defined by linearly extending the map on graded pieces. So what we do is define a ring structure on TV by, if you have um, x belongs to TRV, y belongs to TSV, then x dot y is the image of x tensor y from TRV tensor TSV to TR plus SV. This, remember, was an isomorphism. So the image of x tensor y under this isomorphism. And of course, this only defines multiplication elements which are in these summands, but you can define it for, those are called homogeneous elements, but you can define it for any element just by requiring this multiplication to be a bilinear map. We'll look at it very concretely using some examples. But firstly, what is the unit? So we need to check that this is an algebra, that it's associative, additive, and so on. I won't go into those steps. You can try to check it yourself. But let me just point out that the unit of TV is the element 1 belongs to F, which is T0V. So the unit lives in the degree 0 part, T0V. Let's look at the simplest example of a tensor algebra. Let's take V to be just the one-dimensional vector space F over F. And the basis of V is, let's say, just pick an element. You could take the element 1. But let's call it E. So some element E of F. If you want, you can take the unit of F. Then what is TdV? TdV is V tensor V taken D times. And its basis is just singleton 2. It's just the singleton set E tensor E taken D times. Let's call this E to the D. Just define it to be E to the D. Then E to the R times E to the S is the image of E tensor E R times and E tensor E S times in TR plus S. So that image is just obtained by doing this, and so this is E tensor E R plus S times. So that is E to the R plus S. So what we have seen here is that TV, or let's say T of F, is isomorphic to the polynomial algebra in one variable, which we can call E. This isomorphism is simply defined on basis elements by taking E to the R, or rather E tensor ER times to E to the R here. So the tensor algebra of a one-dimensional vector space is a commutative algebra. It's just the algebra of polynomials in one variable. Now let's look at the more general example, which is basically also the most general example for finite dimensional vector spaces. Every vector space is isomorphic to f to the n. Every finite dimensional vector space is isomorphic to f to the n for some n. So let's just take v to be f to the n. So then this has coordinate basis let's call it e1, e2, en. So ei is the ith coordinate vector. It has 1 in the ith place and 0 everywhere else. And t dv has basis given by ei1 tensor eid, where I1 up to ID, this belongs to, each of these lies between 1 to n and there are d of them. Okay, so this basis is in bijection with words. So consider an alphabet A. So we'll just regard this letter 1 to n as an alphabet. Like in English, you have 26 letters in the alphabet. Let's take a language where you have n letters in the alphabet. And a word in the alphabet is the set of all words in the alphabet A. So a word is just something of the form I1, I2, ID, where I1, ID belongs to n. So this basis is in bijection with I1, ID, words of length d in the alphabet. One to n for j equals 1 to b. So the basis of TDV is in bijection with words of length d in the alphabet 1 to n. You've seen these words in an alphabet before when you studied free groups. So before you constructed free groups, you constructed this object called the free monoid. Let me just recall for you what that is. So the free monoid. Well, a monoid is basically a watered down version of a group. It's a set with an associative binary operation, and that binary operation must have a unit. But the difference between a monoid and a group is that in a monoid we do not require each element to have an inverse. And while trying to construct the free group, the first approximation that you saw was that of the free monoid, and this is exactly what we're talking about here. So an star, as I said, this is going to be, so yeah, maybe just a star is going to be all words of the form ID, I1, ID belongs to n, and d can be greater than or equal to 0. So if d is 0, then there's only one word, namely the empty word of length 0. And the product operation on a star, so it's a function from a star cross a star to a star, is the concatenation product. So concatenation of words means if you have two words, you just write one word and then write the next word after it. Okay, so the concatenation of free and monoid is the word free monoid. So it's just I1, IL. If you want to multiply it with J1, Jm, it's just the word I1 IL, continue on J1 Jm. So this is the word of length. This is a word of length L plus M. This is clearly associative. It has a unit, namely the empty word, but it lacks an inverse. When you have a monoid like this, you can define an algebra. So we'll define the monoid algebra. I'll call it a ring actually. Well, so I'm using the word algebra to denote a ring whose additive abelian group is actually an F vector space and whose multiplication is F bilinear. So you have this monoid algebra, Fan star. So this is an F vector space with basis Ans. Well, maybe I'll give names to those things. 1 sub W, where W is a word in An star. So essentially the basis of this vector space is indexed by elements of the monoid An star. And multiplication, so addition is, it's just a vector space, so you use the vector space addition. And multiplication is defined by bilinearly extending. If you have 1 sub W and you want to multiply it by 1 sub U, then it's just going to be 1 sub W. And then this is defines a bilinear map on basis elements, and so you can extend it to bilinear map on vector spaces. Rather, it defines a function on basis elements, and so you can extend it to a bilinear map from Fan star cross Fan star to Fan star. And this tensor algebra of V of Fn that we saw on the previous page is isomorphic to F of An star via the isomorphism Ei1 tensor Ein goes to 1 sub I1 I. This is easy to see from the definitions. So the tensor algebra is the same as the tensor algebra of the vector space F to the n is the same as the monoid algebra of the free monoid on n letters. Having constructed the tensor algebra of a vector space, a little more work can lead us to the construction of a very beautiful algebra called the exterior algebra. This algebra is the quotient of the tensor algebra by a certain two-sided ideal. So you start with a vector space V and you take its tensor algebra. Let V be a finite dimensional vector space over F and TV be the tensor algebra of V. Now inside this algebra I will take I to be the two-sided ideal generated by vectors of the form V tensor V, where V is in V. Well, tensors of the form V tensor V. So these are all inside V tensor V, which is T2V. Okay, so what do I mean by two-sided ideal generated by a set? It's simply the smallest two-sided ideal that contains that set. To see that it exists, you just take the intersection of all two-sided ideals that contain that set. An intersection of two-sided ideals is again a two-sided ideal. So now I can define the exterior algebra. Wedge V is defined to be TV modulo I. Okay, now before we start studying wedge V, let's look at this ideal I a little more closely. The most fundamental fact about I is that I basically has vectors of this form. For all V and W in V, the tensor V tensor W plus W tensor V belongs to I. This is very easy. It just follows from the fact that I is an additive abelian subgroup of TV. So if you take V plus W tensor V plus W, V plus W tensor V plus W, that's obviously in I by definition of I. It's some vector tensored with itself. But then this is equal to V tensor V plus V tensor W plus W tensor V plus W tensor W. So this is in I. Now among these four terms, this term is in I. So if I remove it also, what remains will be in I, and this term is in I. So what remains in the middle, this is in I, which is exactly what I started off to prove. And we'll use this observation when we are trying to understand the exterior algebra. Okay, so firstly we want to understand the basis of a wedge df of a vector space. So we're going to look at V equals Fn now, and we want to understand the basis of wedge dfn. Okay, so firstly, a first approximation of this is that wedge dfn is spanned by, okay, just to distinguish between vectors in TDN and wedge dn, I will use a certain notation. I'll say VI1 V1 wedge VD denotes the image of V1 tensor VD belongs to TDV in wedge D. So what is wedge DV? It's just the image of TDV modulo I. Okay, I claim that wedge dfn is spanned by vectors of the form EI1 wedge EID where I1, we can take these things to actually be in increasing order. So why is this? Basically, we are going to do certain moves. So we are going to start with a general vector in, so clearly, you know, TDFN is spanned by EI1 tensor EID, where we don't have any order on I1 ID. So they are just elements between 1 to n. And then what we'll say is that by modifying this element TDFN by elements of I, we will be able to arrive at an element where these indices are in strictly increasing order. So the basic idea is the following. So let's look at an example of such a reduction. So suppose you have E3 wedge, E5 wedge, E2. This belongs to T3, let's say F7. Wedge 3 F7. But let's not do that. Let's write it as a tensor product. Okay. E3 tensor E5 tensor E2. This belongs to T3 F7. Fine. And now I can write this as E3 tensor E2 tensor E5 plus E3 tensor E5 tensor E2 plus E3 tensor E2 tensor E5. I have not really done anything here. I have just added and subtracted E3 tensor E2 tensor E5. But let's club these two things together. This is minus E3 tensor E2 tensor E5 plus E3 tensor E5 tensor E2 plus E2 tensor E5. Now in this previous lemma, we saw that V tensor W plus W tensor V is an I for any vector V, vectors V and W in V. So this thing belongs to I. This thing belongs to I, and but then you're left multiplying by something in E3, so this whole thing belongs to I. So what we are saying is that this is congruent to minus E3 tensor E2 tensor E5 modulo I. So by successively interchanging adjacent terms, we can start with E1 tensor EID. We can show that using something similar to the bubble sort algorithm which you may have seen. By successively interchanging consecutive terms in a list, you can take the list and turn it into a sorted list in increasing order. So this is the same as EJ1 tensor EJD, where these J1, J2, JD are the same as these indices E1, E2, I1, I2, ID, but they are written in weakly increasing order. But now suppose two of these indices are equal. If JR is equal to JR plus 1 for some R, then we have this thing EJ1 tensor, and then we have EJR tensor EJ plus R plus 1, which is also EJR, and then some other stuff. But this stuff is in I, just by definition of I, and therefore since I is a two-sided ideal, even if you multiply something in I on the left and right by things in I, you get a two-sided ideal, an element of I. So this whole thing is in I. So this belongs to I. And so this is congruent to 0 mod I. So the only terms that survive are where J1 is strictly less than J2 is strictly less than JD. Therefore, the images, therefore EI1 then EID is either 0 or plus or minus EJ1 wedge EJD, where J1 is strictly less than JD. In wedge D Fn, since the image of a basis is a basis, this is of a basis of a vector space modulo a subspace is a generating set. This is a generating set. So EJ1 spans wedge DFN. Here this should be a plus or minus EJ1 EJD. because each time you interchange two consecutive tensors, sign flips. Okay, now we are ready to prove the somewhat more difficult result, that the image, so this wedge dfn, recall, is the image of tdfn in wedge fn has a basis ei1 wedge ein eid, where 1 less than or equal to I1 less than ID less than or equal to N. This we can call a theorem, and we've already seen that this set spans wedge dfn. We want to show that these elements are actually linearly independent. In order to do that, it's convenient to use somewhat set theoretic notation. So given a subset I of n, write I in increasing order. Let's say I has d elements. Then you write ei to be defined to be ei1 wedge eid. So what I'm basically saying is that collections of strictly increasing indices between 1 to n are the same as subsets of the set 1 to n. And so what we want to show is that ei I subset of n, cardinality of I equals d, is a basis of wedge dfn. Well, the proof goes as follows. Well, what do we need to show? So given scalars ai, I in n, I d, and these ai should be in f, if summation ai ei equals 0, then ai equals 0 for all I. This is what we have to show. So what we'll do is we will multiply this by another element. So let's say fix one of these i's, let's call it j. Okay, and now you take this thing, summation ai ei, and then you, so this is, I leave out the index of summation here, it just gets cumbersome, wedge ej complement. So let's look at this element. So this is equal to summation over I using distributivity ei ai, then ei wedge ej complement. Now if I is not equal to j, then I being a subset of size d and j being a subset of size d as well, so j complement is a subset of size n minus d, I will have at least one element in common with j complement, right? So if I is not equal to j, then I has an element in common with j complement, and so ei wedge ej complement will be 0 except when I is equal to j. So this just becomes summation, no summation, all the terms die out except aj ej wedge ej complement. And by sorting out these elements, we can say that this is the same as ai e1 wedge en. Okay, Firstly, one thing I should have said before is that if n is greater than d, then of course all these if d is greater than n, then of course none of these elements ei can be non-zero. So we are restricting ourselves to the case where d is less than or equal to n. Okay, so we get this ei times e1 wedge e2 wedge en, and I want to show that this vector e1 wedge e2 wedge en is non-zero, because if I can show that, then that means that well, we know that summation ai ei is 0, so then this would imply that ai is 0. So I want to show that e1 wedge e2 wedge en is non-zero in wedge n. So how do you prove this? This is a very interesting proof. It actually uses the notion of determinant. So what I'm going to do is I'm going to show that so this is equivalent to saying that the claim is equivalent to saying that wedge n Fn is not a zero-dimensional vector space. Why is that? Because we know that wedge n Fn is spanned by this vector e1, e2 wedge en. We saw that in the previous lemma. So if this vector is 0, then wedge n Fn will be 0. So this claim is equivalent to showing that wedge n Fn is not 0. But I will prove this, that wedge n Fn is not 0, using determinant. So we have this map determinant, and it's a map from matrices, n by n matrices to F. But I will think of it as a map from TDFN to F. How does it work? If you have a vector V1 tensor VD, then it goes to determinant of the matrix whose columns are the column vectors V1, V2. Sorry, I want this n Vn, because then this is a square matrix and we can take its determinant. So this gives rise, well, so firstly, you know that the determinant is multilinear in the column, so this gives rise to a well-defined linear map from the tensor product, the nth tensor power of Fn, to F. And this is a non-zero map because there are non-zero linear map, because, well, there are matrices with non-zero determinants, such as the identity matrix. And the other fact that we know is that determinant restricted to Tn intersection I is 0. Why is that? Well, this just corresponds to the fact that if you have a matrix, two of whose columns are equal, then its determinant is 0. So this determinant will vanish on any matrix which is in Tn intersect I, because determinant vanishes on matrices with two equal columns. So then what we know is that, so determinant induces determinant bar from Tn mod Tn intersect I to F, and this is non-zero. So determinant gives rise to a non-trivial linear functional from T and Fn mod T and Fn intersect I to F, but this is the same as wedge n Fn to F. So determinant gives rise to a non-trivial, non-zero linear functional on the vector space wedge n Fn. But if the vector space wedge n Fn were 0, it couldn't possibly have a non-zero linear functional. Therefore, we conclude that wedge n Fn is not 0. And therefore, E1 wedge, E2 wedge, En is a non-zero vector in wedge n Fn. So what we get is that 0 is Ai times a non-zero vector, therefore Ai is equal to 0. And hence these, so we can do this for every I, and hence we see that this Ei, as I runs over subsets of size d in n, forms a basis of wedge d Fn. Let us take a closer look at the ideal I. So the ideal I is the two-sided ideal generated by V tensor V, V in V. This is a two-sided ideal in TV. And of course, so this ideal contains all vectors of the form V tensor V, but it also contains tensors of the form V1 tensor, V2 tensor, and then at some place you have a Vk tensor Vk, and then you have tensor Vd minus 1. This would be a tensor in TdV. I claim that the ideal I is actually the span of V1 tensor Vk minus 1 tensor Vk Vd minus 1, where V1 Vd minus 1 belongs to V. As D runs over all well, let's just say D greater than or equal to 1. And this is easy to see because firstly, clearly I would contain all these vectors because it contains Vk tensor Vk and it's closed under left and right multiplication by elements of TV. And secondly, you just see that this span is actually an ideal, so a two-sided ideal. And so I is this span. A consequence of this is that I is the direct sum over d greater than or equal to 0 I intersect TdV. That means I itself is the sum of its intersections with the different degree d components of tensors. And a corollary of that is that wedge V, which is TdV, not TdV, TV mod I is equal to direct sum d greater than or equal to 0 TdV mod I intersect TdV. And this we have seen is wedge D. In fact, wedge dV is 0 if D is greater than or equal to dimension V. And so what we have is wedge Fn is equal to direct sum D equals 0 to n wedge D Fn, and this wedge D Fn is the span of subsets of size D of Fn. So what we have is that finally wedge Fn has basis Ei I subset of n. Now these subsets could have size anything from 0 to n, and you can write down the product of two such basis elements by taking the words, so if you have EI wedge EJ, then you can write down the words, the elements of, so this is going to be 0 if I intersect j is non-empty, and if I intersect j is empty, then this will be plus or minus E of I union j. Otherwise, the sign has to be worked out when you concatenate the words corresponding to I and j, and then you try to sort them back into increasing order. You have to see how many times you have to switch successive terms. So that's the algebra, the exterior algebra, also known as the Grassmann algebra. Now suppose A is a matrix with entries in F. Let's say it's an m by n matrix. Then A defines a linear map, which I'll also denote by A, from Fn to Fm. And what this linear map does is A Ej. So let's take for Fm the basis E1 En, and let's take for Fm the basis F1 up to Fm. And Aej is summation I goes from 1 to m A Ij Fi. So this is the usual way in which we think of matrices as linear maps. Now this A also gives rise to a linear map TFM, TFN to TFM as follows. I'll define it on basis vectors. TA of EI1 tensor EID is TEI1 tensor, not T, AEI1 tensor AEID. This linear map has the property that TA of V1 tensor VD is AV1 tensor AVD for any V1 VD in FM. Okay, so one interesting feature of this map is that if you take something like V1 tensor VR tensor, you have this thing repeated, then this is these kinds of vectors span the two-sided ideal by which we take the quotient to get the exterior algebra. So this is an ideal in this is a vector in I. Just to be specific here, I'll say I F n, and if you apply TD of A to this, then this will be AV1 tensor, and again you'll have AVR tensor, AVR tensor, AVD minus 1, which belongs to IFM. So what we have is that TDA takes IFN to IFM, and therefore TDA induces a linear map which I'll denote by wedge dA from TDA mod IFM to TDA mod IFM. So this is a map from wedge D FM to wedge D FM. So what we've seen is that every matrix also induces a linear map on the exterior algebra. So the question I want to ask now is, what is the matrix of this linear transformation wedge dA? What do I mean exactly by that? What I mean is that you take this wedge dA, and so this wedge dA goes from wedge dFn to wedge dFm, and so we take a basis vector of wedge dFn. So we take so we had taken for the basis of Fn, we had taken E1, E2, En. So we take a basis vector for this would be of the form Ej for some j subset of n. And then this is a vector in wedge dFm, and so we expand it in terms of the basis that we have for wedge dFm. So this is going to be summation over I subset of m Aij Fi. So this system of constants Aij indexed by i's subset of m, j subset of n, I'll refer to this as the matrix of wedge dA. If you somehow order the subsets of m and the subsets of n, maybe here these are size of I is d, size of j is d. So if you take all the subsets of size d and order them somehow, then this becomes, you can really write this as a matrix whose the number of rows will be m choose d and number of columns will be n choose d. So you can think of this as an m choose d times n choose d matrix, but let's just think of it as a system of coefficients defined by this equation here. For every subset g of n. Okay. So to figure out this matrix is not very difficult. So let's just unwind the definitions. So what happens if we start with wedge dA and then apply it to Ej1 wedge Ej. So we started with a j, which is a subset of n d. Well, by definition this is going to be Aej1 wedge Aejd. Okay, now let's expand all these things. So this first thing is going to be summation I1 equals 1 to m A I1 J1 F I1 wedge I2 equals 1 to m A I2 J2 F I2, and so on up to ID equals 1 to m A ID JD F ID. And if we pull out all the constants, we'll get this multiple sum I1 equals 1 to m, I2 equals 1 to m, ID equals 1 to m, and then we get this product of coefficients I1 J1, AI2 J2, AID JD, and then finally we get our vectors, which are FI1 wedge FID. But I want to, these things are not linearly independent. If I take some of these vectors and if two of them, if two of these i's are equal, then it's going to be 0 in wedge D of Fm. And also if these are not in increasing order, when I reorder them, there will be a sign change. So if I account for that, I can rewrite the sum as sum over 1 less than or equal to I1 less than I2 less than ID less than or equal to M, and then all the possible reorderings of the vector. If two indices are the same, then this thing is 0, so I don't worry about those cases. But all possible reorderings means I need to go over permutations in SD, and every time I interchange two of these factors, there's a sign change, and that corresponds to the sign of the permutation W in SD, and then I get AI W1 J1 AI WD JD. But this, and yeah, this is the coefficient of the term FI1 FID. So this is exactly what we were looking for. So we were looking for the coefficient of such a term. Therefore, Aij is precisely the determinant. This thing here is a determinant. It's a determinant of what? A submatrix of the original matrix A. It's a determinant of the submatrix of A obtained by choosing rows according to the subset I and choosing columns according to the subset J. So what we have is the formula: wedge D A applied to Ej is summation I subset of M determinant of Aij Fi. So this is the formula which shows how wedge dA acts on wedge D Fm. So this determinant is what is often called a D by D minor of the matrix A. So what I'm saying is that the matrix entries of the linear map wedge dA are the D by D minors of the linear map A itself. Now suppose I have two matrices. A belongs to M, M by MF, B belongs to, let's say, M by NF, and B belongs to M, N by LF, where M, N and L are three possibly different positive integers. Then you can multiply these two matrices and AB will belong to AM by LF. And so we have TA from TFN to TFM. We have TB from TFL to TFN. And what is clear from the definition of TA and TB is that T of the product matrix AB is TA composed with TB. Just see how it acts on basis vectors. And so also wedge of AB is wedge of A composed with wedge of B. Okay, so now let's see how these are related to the matrices. So suppose you take some K subset of the set 1 to L and the size of K is D, and we ask what is wedge DAB when it is applied to EK. Okay, this is on the one hand given by D by D minors of the matrix AB. So this is summation I subset of M, determinant of AB IK Fi. On the other hand, it is a composition of matrices of minors. So on the other hand, this is wedge dA applied to wedge dB applied to EK. But this is just wedge dA applied to summation J subset of N, determinant of B JK, the minor of B corresponding to rows J and columns K, EJ, just by what we did earlier. And then we apply wedge dA to this and we get summation over I subset of M, summation J subset of N, and then we get determinant of A subscript IJ, determinant of B subscript JK F. Maybe I shouldn't have called this EK, let's call it GK. So let's take F to the L has basis G1, G2, GL. Then, yeah. Fi. So the conclusion that we draw from all this is that the determinant of, you take the product of a matrix and take its I, kth D by D minor, where I and K are subsets of the rows and columns of, I is a subset of K is a subset of L and I is a subset of 1 to M. Then you get that this is sum over all subsets J of N of size D, determinant of Aij, determinant of Bjk for all I of size D, K of size D, I subset of M, K subset of N. This beautiful identity involving minors of a product of expressing the minors of a product of two matrices in terms of the minors of the matrices themselves.